Hi guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at the steam tables and what's called linear interpolation. Now before we start, I would just like to introduce a fantastic new competition that we're having whereby you can win £500 every month for a year simply by answering a simple question. But we'll talk about that at the end of this video, so be sure to watch all the way through till the end. So the first question here is, what exactly is a steam table? Well, in simple terms, a steam table is a set of thermodynamic data that contains the properties of water or steam. Now these data are commonly used by a multitude of engineers, but for us as chemical engineers this is an integral part of thermodynamics and heat transfer. Now it is normally used in order to obtain the following sets of properties that we'll look at in just a second for given sets of saturated temperatures and saturated pressures. So we'll talk more about saturation a little later on. So the question is, what exactly do these look like and why do we really need them? Because we've noticed that it's to do with thermodynamics, but what is actually the point? Well, as chemical engineers, we need the steam table in order for us to obtain the physical properties of water, or indeed there are some other compounds such as ammonia and other derivatives of that sort at a range of different operating temperatures and pressures. So because our systems will change, we want to know what the physical properties of the fluid will be at these given different operating conditions. So the steam table will provide us with a series of data with a range of temperatures and pressures. Now, we are going to assume here an idealized behavior, which therefore will indicate that the temperature and pressure are directly related to each other in the form of a straight line. So it's near enough a straight line, so we approximate it to an ideal gas system. So essentially what it means is, if we know, say, the gauge pressure, we could draw up a straight line and then interpret it across, and that would give us the corresponding saturation temperature. So again, it comes back to this idea of saturation, and we'll look at a phase diagram to see exactly what is going on in terms of saturation and unsaturated. Now this allows us to approximate what the saturation temperature would be for a fixed saturation pressure, or vice versa. Now this is a screen grab of a typical table that you would find within a steam table. Now it's called a steam table, but it's actually a book that contains just several different renditions of tables like this. It's full of numbers and it gives us a lot of very important information. But on first inspection, it may look a bit overwhelming because you just have these plethora of different numbers. But trust me, when you go through this, we break it down, it's actually very straightforward. Now, these are the two columns that we will use initially to fix our operating system. So we have temperatures in the first column. Now, this one only goes up to 52, but the other pages within the steam table, and I'll put a link in the description to the online reference of the steam table, along with another couple that you can check out if you need them for your own use, or if you're just curious to see what the other tables look like. But in this case, we're fixing these temperatures and allowing the saturation pressures to be slightly, they aren't exact fixed values. So what you'll find is in the other tables, we actually fix the pressures to be very, specific values, and we let the temperature take the leeway. Now we have a series of different parameters here. We have 3 columns that contain V, 3 columns that contain H, 3 that contain U, and 3 that contain S. Now we're going to define these in just a second. But we can actually pick up trends here. So as we move down in terms of V, we can see that the value gets smaller. And this is replicated for both VF and VG. So again, we just need to, you can analyse this data as much as you possibly want to get an idea of the interaction between the temperatures and these given variables. But at this moment in time, we aren't really interested in doing that kind of analysis. What we want to know is what are these different parameters and how can we use them in examples. So let's first define what the subscripts of F, G and Fg stand for. So F, so when we see in here that these F values, so that's what we're talking about, so HF, VF, UF and SF. So what these mean is this is for saturated liquid. So if we have a saturated liquid system, then these would be the values that we would use. If we had G, this would be for saturated vapour. So say we're working with saturated vapour at 25 degrees, then that means we're going to have an extremely high pressure. Now Fg is basically the change of the phase at a constant pressure. So again, we can manipulate this ever so slightly. We can have correlations whereby it doesn't necessarily have to be in terms of pressure. We could actually express it in terms of something else. But in essence, Fg is the change of the phase from saturated liquid to saturated vapour, or vice versa, at a constant pressure. So what does the steam table actually tell us? Well, V, so normally denoted by lowercase or uppercase, it doesn't really matter. Here I'm just going to denote it by capital, just so that it stands out. But sometimes on the tables it will be denoted as lowercase. So V is known as a specific volume, i.e. what is a specific volume of saturated liquid or saturated vapour that this system will enclose for that either saturated temperature and pressure system. So if we take a quick look here, so we can see it's meters cubed per kilogram. So we can see that at 0 degrees and a fixed saturation pressure of 0.6119, we can see that the specific volume of saturated liquid is essences much lower than that of saturated vapour. So that makes sense because the vapour will occupy a slightly higher volume. Now, moving from V, H is known as the specific enthalpy. Now, enthalpy is a term that we should be familiar with as chemical engineers. If you're not, then please do check out our other videos on thermodynamics, whereby we talk about specific enthalpy. U is known as the specific internal energy, so sometimes abbreviated to the overall heat transfer coefficient. And then S is known as the specific entropy. Now, entropy is essentially a measure of disorder. So this is, say for example, a solid will have a lower entropy than, say, a gas, because the level of disorder is much higher. Now, this tends to be a chemistry principle, not so much an engineering principle, but it's just something that we need to keep in mind. So, say for example we wanted to combine what these parameters mean along with these variables. Then if we were to express HF, what that would mean is the specific enthalpy of saturated liquid, because F subscript is the saturated liquid and H is the specific enthalpy. Likewise, if we have Sg, we have the specific entropy of saturated vapour. And say we have VFG, then that is a specific volume of a phase change. So that would be the phase change from saturated liquid to saturated vapour. So that's what the symbols mean, and that's how we obtain that very important data from the steam tables. Now, as I mentioned before, and I talk about it quite a lot here, is the phase diagram. And the phase diagram is basically a thermodynamic representation of how we can distinguish between the saturated vapour, the liquid, and the multi-phase system. So a typical example here looks something like this. Now, we can have these in several different types of plots. So here, what we're doing is we have the temperature versus the enthalpy. And these lines, so this big black line here, this is the constant pressures. Okay, so what we can have is we can change these depending on the system that we want. So for example, we could plot temperature against entropy rather than enthalpy. But essentially what we say here is anything that lies to the left, so this big curve here, anything inside of this is known as the two-phase region. So what that means is that liquid and vapour will exist simultaneously. It doesn't mean in the same quantity, it just means that they will exist at the same time. Whereas anything in this kind of dark blue area, or anything to the left of the two-phase system, is saturated, in this case water. So that means that there is no vapour in this entire region. There is no vapour at all. Anything to the right of the saturation line is saturated vapour. So anything here, there is no liquid within the system. It is all 100% vapour. Now we do have what's called the subsaturated and the superheated regions as well. So that just means that we can take this a step further. But we look at that in a lot more detail in our thermodynamics course. So if you're really interested in that, I'll put a link in the description and you can check that one out if you get the chance. It's a very interesting and very in-depth course, and this is what my master's thesis was on. I basically designed several different types of organic Rankine cycles, thermodynamic cycles for waste heat recovery systems. So this is right up my street in terms of what I've done for my master's degree. So again, if anybody's interested and they want to learn more, please feel free to drop me an email or put in the comments, and I can also look to maybe make a series on, you know, my history as a chemical engineer so far. But anyway, back to the phase diagram. So anything that lies on this line is known as saturated. So anything to the left of the critical point on this black line is saturated liquid. Anything on the black line to the right is known as saturated vapour. So very, very straightforward. So that's what it looks like on a graph. Now let's take a look at a couple of examples here. So it asks us to evaluate the enthalpy of 10 kilograms of saturated steam at 1 bar and determine its saturation specific volume. So what we need to do here is we need to bring up the steam table. Now you can see that this begins at 54 degrees and goes to 110. So this is actually page 2 of that reference steam table. Now we just need to be careful because we were given our pressure here in bar, whereas here we're in kilopascal. So that means that 1 bar is equivalent to 101.325 kilopascals. So what we need to do here is we need to go down to our steam table until we find that corresponding pressure. So you can see here, this is the pressure here. So we work along this row. Now the question says that we want it for the saturated specific volume and saturated steam. So saturated steam refers to the saturated vapour, i.e. Hg. Okay, so that means that we would come here, we'd come down this column, and we can see that the saturated enthalpy, the enthalpy for saturated vapour is 2675.84 kilojoules per kilogram. And then the saturation specific volume for the saturated steam, that will give us is 1.673 meters cubed per kilogram. Now the question asks us for 10 kilograms. So that means that we would have to multiply both of these by 10, and that would tell us that the saturated specific enthalpy is 26,758 kilojoules, and for the saturation specific volume we get 16.73 meters cubed. And that is literally as difficult as it can become in terms of just reading straight off from the steam table. Now, as I mentioned at the start, we're going to look at something called linear interpolation. Now, linear interpolation is not just restricted to steam tables. We can use it in pretty much any mathematical relationship that we want. But essentially, linear interpolation is a method that will allow us to determine an unknown value based on a set of data that's slightly above and slightly below our target value. Now, it's a convenient way of finding these unknown values for data points that aren't readily available. So, say for example, we have a temperature within the steam table that isn't registered there, so it's not got its own independent data set. Then what we would have to do is perform linear interpolation against the value that's slightly below and the value that's slightly above. It's basically like trying to take a numerical average between them. Now, there are several renditions of the interpolation formula. However, for general purposes, here is an example for the enthalpy temperature relationship for interpolation. So what this means is that we have the enthalpy, the target enthalpy that we want. Then what we do here is, so T1, or the value of 1, is the value just below, and the value of 2 is the value just above. So that's what these subscripts mean. So for the enthalpy or target enthalpy, what we are saying here is we take the lower enthalpy plus the ratio between our change in temperatures, so that's the actual temperature that we are operating at for this enthalpy, minus the lower temperature, divided by the upper temperature minus the lower. Then we multiply this by the change between the upper and lower enthalpies. And that there would give us the enthalpy of our target temperature. So let's take a look at an example on how we would use linear interpolation. So we need to find the enthalpy of 1 kilogram of saturated steam with a volume of 2.2 meters cubed. So because we can't find exactly this value here of 2.2, we'll need to do linear interpolation, alright? Because we can see we don't have exactly 2.2 here. So that means that we'll need to take a value that is slightly below, and a value that's slightly above. Because we can see that between 2.217 and 2.087, the value of 2.2 will of course lie in here. So we'll say at 0.75 bar, this will be 0.1. So this is the lower value. So we say that Vg, so that's the specific volume, is 2.217, and the specific enthalpy is 2662. Now we do the same thing for the upper point, so that'd be 0.8. So we get Vg is 2.087 and Hg is 2665. So again, we just read these from the steam table directly. Now we don't know what the temperature is. So like in the general formula, we don't actually know what this temperature is. So we have to use the pressures and the specific volumes. So first things first, we will make a note of all the information that we have. We'll just summarise it. So we have the pressure, the enthalpy and the volume for 0.1. We have the volume, the pressure and the enthalpy of 0.2. So here we want to know what the enthalpy is for 1 kilogram of saturated steam, so Hg, at 2.2 meters cubed. So this is what the 2.2 means. So our general formula is going to be our lower enthalpy plus the change in the upper and lower enthalpy divided by the change in the pressure, so that's between the upper pressure and the lower pressure, multiplied by the lower volume minus our target volume. And our target volume is 2.2. So all we do here is substitute in these values into this general equation and we begin to solve. So from here, we just simplify our system, and that will tell us that the enthalpy for 1 kilogram of saturated steam that corresponds to a volume of 2.2 meters cubed will give us 2662.4 kilojoules per kilogram. And that's how you would go about solving linear interpolation for steam table problems. Now, as I said before, we are proud to introduce a new competition that we're having. So this starts from this video moving forward. And the competition sees that one person each month will be selected at random to win £500 every single month for an entire year. So all you have to do here is answer this very simple question correctly, comment your answer in the video, like the video and subscribe to the channel, and you will be in with a chance of entering. Now, the more videos that become available, the more entries that you will have. Now, only valid subscribers with the correct answer will be entered into the draw, and you will see the results of the draw on our Facebook page. So be sure to subscribe to the Facebook channel. I'll put a link in the description to that so as that you can see the results. Now, the question here is, specific what does not change during a phase change when the temperature and the pressures are kept constant? So we want to know specific what. What is that parameter that does not change during a phase change when the temperature and the pressure are kept constant? So once you know the answer, comment your answer, like the video, subscribe to the channel, subscribe to the Facebook channel, and you will see and be in with a chance. This first draw ends on the 31st of August 2022, so make sure that your entries are in beforehand. So best of luck, and I look forward to seeing your answers in the comment section. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding the idea of the steam tables in linear interpolation. If you liked this video, please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and good luck in the new competition, and we'll see you in the next video.